Hey champs, welcome back to all of you once again on your channel, that is on JEE Physics Maniac. I hope all of you are fine. The threat is looming over, so I hope all of you are taking proper care, precaution, and do not be too much anxious about the fact that when JEE Main is going to be conducted, whether it will be deferred or not, the things will take its own course. You should not be too much disturbed. Stay focused. So, in today's session, we are not going to discuss, I'm not, can I say, uh, very tedious thing. It is a kind of revision exercise, and I will try to bring in such kind of videos very frequently, which will help you in this time just before examination. This will be revision kind of videos. I will bring in one concept or sometimes two, three concepts put together so that you are just able to recollect and remember the things that you have already done. So in today's video, we will see few cases of rigid body collision, and we are going to see the cases when the rigid bodies are not hinged. Okay, and then I will take the examples of the hinged rigid bodies also in subsequent intervals of time. So without wasting much time, let us proceed. So in the first case, you can see that there is a rigid massless rod of length L joined two particles each of mass m. So these two are mass m. It is joined by a rigid rod of length L. And another mass is moving towards this mass m with velocity v naught. It is being said that after collision, the projectile moves straight back. So that means right after collision, this mass m, here in the diagram you can see, it will move back with some kind of velocity. Now that velocity they did not mention, what is going to be the velocity, that they didn't say. So we cannot speculate about what velocity with which it is going to return. We have to see it scientifically. And they're asking find the angular velocity of the rod about its center of mass after collision, assuming that mechanical energy is conserved. Now, see, all these questions are essentially based on three main strongholds or three pillars, three conservation laws. One is the conservation of linear momentum, another is conservation of angular momentum, and another thing is conservation of energy. Right. So, here I will discuss quickly a short point. Later, I will come with a brief discussion. Suppose there is a rigid wall. If I take in a rigid wall, if a ball is approaching the rigid wall, it is hitting the rigid wall and then it is coming back from the rigid wall. In this particular case, we know in each kind of collision, linear momentum is conserved. So I will keep you with a puzzle that do let me know in the comment box if the ball is going to hit the wall in this direction and after collision the ball is bouncing back and by that time the wall remains fixed, how the momentum is conserved. We all write the conservation of momentum equation, but we don't think about the technical part of it. So think on it. Anyway, so moving ahead, here in this case, we will apply three conservation laws. One is conservation of linear momentum, another is conservation of angular momentum, another is conservation of energy. So right after collision, I will remember that this entire system comprising these two masses and the rod will move with velocity v, and this velocity is the velocity of the center of mass of the system, right? And the ball will bounce back with velocity vf that we have already seen in the diagram. So if I write the equation, I will simply write that mv naught plus this entire system was at rest, so I can safely write 0 plus mv naught is equal to minus mvf. This minus sign is coming because of the direction, plus 2m into v. So from conservation of angular momentum, I will write very simple equation mv naught into L sine 45 degree. Here you see, it's a very interesting point actually. We are considering the fact that this is rotating about the center of mass, correct? And I am taking this point here. All right. So if I take the reference point, then mv naught into L sine 45 degree is equal to minus, because this ball is moving in the opposite direction. So about this point, the direction of angular momentum will change if you apply right hand thumb rule. So that is minus mvf sine 45 degree into I omega. Here I we are measuring about the center of mass. And from the conservation of energy, we will get simply kinetic initial is half mv naught square plus 0 for the rod and the masses. Finally, for the ball is half mvf square plus half I omega square. So if we solve these three equations, you are going to get the answer. That's a very simple thing. So let's proceed for the next example. So here you can see that there is a plank of length 12 of mass capital M lies on a frictionless plane, and a ball of mass m speed v naught strikes its end. Right here the ball is striking at the end. So what the outcome? They're saying find the final velocity of the ball Vf assuming that mechanical energy is conserved, and the velocity of the ball after collision is along the line of original motion, right? Um, that is part A, and part B they are saying that find Vf assuming that the stick is pivoted at lower end, right? So let's forget, first let us consider that the stick is free. So again, conservation of linear momentum, mv0 is equal to minus mvf plus mvp, right? Then conserving angular momentum, same thing, mv0 into L minus of mvf into L plus I0 into omega. And conserving mechanical energies, half mv0 square is equal to half mvf square plus half mvp square. This entire is basically the kinetic energy of the rod. So the rod is rotating as well as translating. So the point that you have to remember over here is that if the rod is not hinged, then take the rotation about center of mass of the system, right? So if I solve these equations, we will get the answer Vf is equal to V0 into 1 minus 4m by capital M divided by 1 plus 4m by m. In the second case, if the rod is hinged at this point, then obviously it will rotate about this point. Now there are few very important points to be remembered that you have to remember, and I have noted it down, you can read it, that because of the forces acting on the hinge, linear momentum of the system cannot be conserved. So this is a very, very interesting point. So here, one of the three conservation laws will be omitted. And which one will be omitted? The omission will come from conservation of linear momentum. But angular momentum will be conserved. Why? Because essentially, the hinge reactions will act through this point. So if they are acting through this point of hinge, they will not generate any torque. So in the absence of external torque, angular momentum will be conserved. So from that conservation, we can write mv0 into 2L is equal to minus mvf into 2L plus ip into omega. And this is the point B, the hinging point. Conserving mechanical energy, it is the condition given in the question. So we will get the answer Vf is equal to V0 into 1 minus 3m by capital M divided by 1 plus 3m by capital M. This is second type. Let us move on for the third type. What they are giving? That a boy of mass m runs on ice with velocity v0 and steps on the end of a plank length L, mass m, which is perpendicular to the path. Describe quantitatively the motion of the system after the boy is on the plank, neglect friction with ice. Second point, one point on the plank is at rest immediately after collision. Where is it? So we'll do step by step. First step. So first figure out the center of mass of the boy plus plank system. So I can simply apply the equation that m1r1 plus of m2r2 divided by m1 plus m2. So if I apply that equation, I will easily get that it is capital M into L by 2. Why? Because for the rod, the mass will be concentrated here. So if I take this as the reference point, I can take bottommost point also as reference point because the ball is hitting here. So at a distance of L by 2, the concentration is of capital M and small m is at this point because we are fixing coordinate here. We are fixing the coordinate at the origin. So the small m is at 0 and capital M is at a distance of L by 2 from here. So that is capital M into L by 2 divided by small m plus capital M. Second step is to figure out the velocity of center of mass. Same formula as you all know, m1 v1 plus m2 v2 divided by m1 plus m2. And here in this case, this ball is in motion, rod is at rest. So if the rod is at rest, VCOM becomes mv0, small mv0 by m plus m. Initial angular momentum only the small ball was having, so this is mv0 into x. Final angular momentum is ix into omega. What is x here? X is the distance of the center of mass from the bottommost point. Please be careful, it is not an L by 2. The center of mass is somewhere here. So that means this is the distance x, right? So x is the distance from this end point to the center of mass. Now I have to figure out the moment of inertia about point x. So for that I have to use the parallel axis theorem, and I have done this calculation which you can easily understand. I am not going to explain the calculation, that you can do very easily. So from that, solving these equations, you will get omega is equal to 6 into small m by capital M plus 4m into v0 by L. So that is going to be the answer for part 1. In part 2, they are asking that one point on the plank is at rest immediately after the collision. Where is that point? So if I have to figure out that which point is at rest, I have written this line here. The point which is at instantaneous rest must move anti-parallel to center of mass with velocity v such that v net becomes 0. So it's a very, very interesting point. So if you want that point to be at instantaneous rest, the center of mass of the system has a certain kind of velocity. Now that particular point where we are trying to figure out the zero velocity must move with the equal velocity in anti-parallel direction. So what I'm simply taking that from the center of mass, let us take this point is at distance y. So v is equal to omega into y, that is the velocity of this particular point. So y we can get v by omega. Now point is, we already got the value of v, we already got the value of omega. If I substitute, y is going to become L by 6 capital M plus 4m divided by capital M plus m. So these questions that I have discussed over here, this particular question and this particular question, they are the perfect candidate for paragraph type question or matrix match kind of question. So I hope things are clear with you. You got a thorough and brief understanding of the thing that what can be done in case of rigid body collisions. Right? We have discussed 3 cases. In 2 cases, we have seen that if the body is free, then what are the conservation laws to be trapped with, and in case if it is hinged, which particular conservation law we have to draw. Right? So I hope this is helping you enough. And by the way, thank you very much for helping me to reach out more than 780 plus subscriber. Now it is around 787. So I hope in this rate I will reach 1000 subscriber and the journey will be there in the future. It's not going to be smooth, but definitely I will be with you till that time. Keep supporting, keep watching, keep sharing. Thank you.